Okay, let's get started. So, so we're in the middle of talking about, well, we just started talking about linear transformations, right? Somebody would tell me what makes a linear transformation a linear transformation? What is this property, right? So linear transformations. You have some map from one vector space to another, and then it has two properties, right? What are those two properties? Lizzie.
The transformation in V of vector 1 plus vector 2 equals the transformation of vector 1 plus the transformation of vector 2 in space W.
Right, so T of V1 plus V2 turns into T of V1 plus T of V2, right? And then the other one is T of alpha times V is alpha T, right? So they are two properties that deal with the addition and the scalar multiplication, right? The basic operations of vector spaces, right? Okay, these two properties are called linearity. I didn't mention it, but that's what we call them. We say, you know, a function is linear if it satisfies these two things. Okay, so we're actually going to do a bunch of exercises in this class at least at the beginning. Okay, so we'll start off. So here's a lemma. This is a pretty important lemma. It says that if T1 and T2 are linear transformations, let me say it this way. Say T1 and T2 are linear transformations. If they agree on a basis, and what I mean by that is if there exists a basis V1 Vn such that T1 of Vi equals T2 of Vi for all I, then T1 of V equals T2 of V for all vectors in your vector space. Okay, so if they agree on a basis, if they agree on the basis elements, then they agree on every element. So let me say it again. You've got these two vectors. You've got these two linear transformations, and you have a basis. And on each element of the basis, the two transformations give the same result. Okay. On each element of the basis, right? On each element of the basis, the two transformations give the same result. Then they're going to give the same result on every vector in the whole space. Every vector in the space. Okay, so think about it for a minute and see if you can explain why that happens. Okay, talk about it with somebody nearby. I realize that's not as easy as usual today.
Right, so yeah. Yeah. It just says right.
Okay, would anybody like to explain it? So what's the proof, right? Right, we want to show that for any vector in your vector space, T of V1, sorry, T1 of V equals T2 of V. Right? Why should that happen? Why should that happen? Somebody have an explanation? Sherry, how about you? You don't know, that's okay. Stella, how about you? No? Okay. Lizzie?
Well, any V in the vector space is going to be like alpha times one of the bases, or like one of the bases plus another one of the bases.
Well, so it's true that, right, this is a basis, right? So everybody in V is a linear combination of these guys.
Yeah.
Right? Everybody, each V, so let me see. Pick any V in V, right? Since the VI are a basis, we know that this V must be some linear combination of them, right? Alpha 1 V1 plus alpha 2 V2 plus alpha n Vn for some alpha I in R, right? The span of the VI, the span of the VI is the whole vector space, right? Okay, so then, so we want to say, so why is it true that T of V, I'm sorry, T1 of V equals T2 of V, right? So why is T1 of alpha 1 V1 plus alpha n Vn equal to T2 of alpha 1 V1 plus alpha n Vn? Right? That's what you want to show, right? That T1 of V equals T2 of V. So you said it's a linear combination of these guys. Well, why should these things be equal? Anybody see it? Stella?
So if you multiply T1 to every vectors
In the sum?
in the sum,
Uh-huh.
and you get alpha T1 plus T1 alpha V2, which is equal to T2 alpha V1.
Okay, great. So you say, well, look, by linearity, I can break this up. Well, by linearity, T1 of alpha 1 V1 plus plus alpha n Vn equals T1 of alpha V1 plus T1 of alpha V2, alpha 1 V1 plus alpha 2 V2 plus T1 of alpha n Vn. Right, by the first part of linearity. Right. So we can do the addition later. Okay. And then by linearity part 2, right? By part 2 linearity, we can pull the constants out, right? By part 2 linearity, we can pull constants out. The alpha 1 can come out. This becomes alpha 1 T1 V1 plus alpha 2 T1 V2 plus alpha n T1 Vn. Right? But, like we said, like Stella said, right? This is the same thing as alpha 1 T2. We know that T1 and T2 agree on the basis, right? T1 and T2 agree on the basis, so this is the same thing as T2 of V1 plus alpha 2 T2 of V2. I can switch everything to switch everything to T2. Right? By hypothesis. Right? Because we assumed that was part of our hypothesis, right? That T1 and T2 agree on the basis. Right? That's this link here. Okay. And then we can put everything back together, right? We can get back to T2 of V by just reversing what we just did, right? So again, we can slide the alphas back in. This becomes T2 of alpha 1 V1 plus T2 of alpha n Vn, which is T2 of alpha 1 V1 plus alpha n Vn. But that's just V. Okay, so we use linearity again backwards, right, in the reverse order. Okay. Anybody have questions about that? Anybody have questions about that? Okay. This result is going to be really useful. We're going to use it all the time in the next section, next couple of sections. Okay. So keep it in mind. If you've got two linear transformations and they agree on the basis, then they're the same linear transformation. Okay. If they agree on a basis, they agree on all vectors in your vector space. Okay. Okay, let's go on to the second idea. So second important idea. So again, you have a linear transformation. Again, you have a linear transformation. We say that this linear transformation is 1-to-1. 1-to-1 if whenever T of V1 equals T of V2, we have that V1 must be V2. Okay. Whenever T of V1 is T of V2, then V1 and V2 must be the same. Whenever the outputs are the same, then the inputs must be the same. Okay, let me give you a non-example. The other day, we looked at this map, which was T from R2 to R2. And what it did was it took x, y, and mapped that to x, 0. Right? It was the projection onto the x-axis. Right? Right? So you take your vector, and you take the projection onto the x-axis. Right? So you have your vector, and you have your t of your vector. Okay. You see that there are multiple vectors that would end up with the same output, right? There are multiple vectors that would end up with the same output, right? Like if I had this guy, right, from the same x coordinate, well, it would also get projected onto the same thing, okay? And so T of V1 and T of V2 are the same, but the inputs are not the same. The outputs are the same, but the inputs are different. Okay, so this is not not a one-to-one map. Okay, not a one-to-one, not a one-to-one linear transformation. Okay. Maybe for an example, you could think of the coordinate map, coordinate vector map. So remember, you have some vector space, V a vector space, and V1, Vn a basis, right? Then you have this map. You take some vector, and then you map it to the coordinate vector. Let's call this thing B. Let's call this thing B. Sorry. You have some vector, and then you map it to its coordinate vector with respect to that basis, right? You remember what that is? That's the vector of coefficients that you use to get the linear combination that gives you V, right? Right. V would be C1, V1 plus C and Vn. Right. You express your vector as a linear combination. You take those coefficients. You make that vector. That's your coordinate vector. Okay. Okay. Well, if two guys had the same coordinate vector, what does that tell you about the original vector? If they have the same coordinate vector, what does that mean? Well, then they both have the same linear combination, right? Well, then they must be the same vector. Okay, so if two, right, if V with respect to B and W with respect to B have the same coordinate vector, right, that means that V and W must be the same, right? So this is a one-to-one, this is a one-to-one map. Everyone getting some idea of what one-to-one means? Okay. Right. Or maybe here's a simpler example. Right. If I have an invertible matrix, if I have an invertible matrix and I talk about the left multiplication by A, right? If TA of V and TA of W are the same, then V and W must be the same vector. Right? Because if AV equals AW, then V and W have to be the same. If TA of V equals TA of W, that says that AV equals AW. Well, why are V and W the same? How would you show that V and W are the same? Taki?
Because A is invertible.
Because A is invertible, exactly. So you just invert on both sides, right? So. So here's, okay. Okay, let me give you the important exercise. Okay. So here is another exercise. Maybe we'll call it Lemma. t is 1 to 1 if and only if the kernel of t, so you have t, a linear transformation, if and only if the kernel of t is 0. T is 1 to 1 if and only if the kernel of t is the 0 vector. Okay, so take a minute and see if you can prove either the forwards direction or the backwards direction or both of them. I feel like you guys may be the only students working right now. I don't see any other classrooms open.
There's one at the other end of this room.
Huh?
There's one at that end.
Oh, yeah,
Of this
okay.
side.
Yeah, the biologists.
So I think this one's
Okay, actually, let's think about this together. So let's think about the forwards direction first, okay? So proof of the forwards direction. Okay, so we're trying to show that the kernel is 0. What's the kernel? Let's remember, what's the kernel? Somebody? Yok, what's the kernel?
I'm not sure.
Not sure?
Yeah.
Remember, it's something like the null space. Do you remember the null space?
Yeah. So it's we in vector space. There exists V in vector space whether T V equals 0.
That's right. Anything that this vector, this transformation sends to 0, right? This guy is all the vectors such that t of v equals 0. Okay. So we're trying to show that the kernel is 0. In other words, that the only thing that this guy sends to 0 is 0. Okay? Right? So we need to do a little bit of translation, right? What does this mean? We want to say that 0 is sent to 0, and it's the only thing that's sent to 0. Okay? So, so first off, we notice that, notice that t of 0 is 0, right? That's just because we have a linear transformation. Remember, that was the first of the boring properties that we proved the other day. Okay. So we know that 0 is in the kernel. Okay, right? We know 0 is in the kernel. Now we have to show that 0 is the only thing in the kernel. Well, why is it the only thing in the kernel? Julia?
Because 1 to 1 means that there's only one, I guess, input that gets mapped to
Exactly.
each output.
Okay, yeah, exactly. So since t is 1 to 1, right, since t is 1 to 1, right, if t of v equals 0, since t of 0 equals 0, right, then we'd have that v must be equal to 0, right? If t of v equals 0, we already know t of 0 is 0, so they must be the same, right? the outputs are the same, means that the inputs must be the same. So one-to-oneness gives that to you. Okay, great. Okay, so now let's think about the opposite direction. Well, suppose we know that the only thing that is sent to 0 is 0. Okay, 0 is sent to 0, but it's the only thing that's sent to 0. So we know that 0, t is 0, we know that 0, so assume that the kernel of t is the 0 vector. Okay, and we want to show that if t of v equals t of w, then v and w must be the same. Right? If t of v equals t of w, then v and w must be the same. Okay. You say, well, okay, let's say that t of v equals t of w. Okay. Remember, we have only one fact, right? That the kernel of t is 0. Right? That is, the only thing sent to 0 is 0. Well, can you make t of something equal to 0 out of this? We have to use that fact. So let's force it in there. Right? Let's bring it in there by turning this into something that says t of something is equal to 0. How do you do that? Yo. No. Sorry, I thought you look like you knew, but I have no idea what you know.
You said t of something is equal to 0?
Yeah. Can we take this and turn it into t of something equals 0?
Isn't it just t of 0 equals 0?
That we know, but I want you to use this fact. Right? We want it. The fact that we have is that if t of something equals 0, then that v equals 0. Right? That's our information. That the kernel is 0. Right? The only thing that gets sent to 0 is the 0 vector. Okay. Can anyone see how we can use this plus this to get that v and w must be the same? Sure. Julia?
Can we use that t of v minus v equals 0?
Oh, you're so close. T of v.
Like plus or minus t of w?
Exactly. Then t of v minus t of w is 0. Right? And then t of v minus w equals 0. Right? By linearity. Right? So by linearity. Exactly. Right? But we know that the only thing that's sent to 0 is 0. Right? So v minus w must be 0 since the kernel of t is the 0 vector. Right? But that tells you that v and w are the same. Okay. So this is sort of like, do you remember back in pre-calculus, you learned about one-to-one functions and inverse functions, right? If you have a one-to-one map, if you have a one-to-one function, you can have an inverse function. You have something called the horizontal line test, right? Right? That tells you if your function can be inverted, has an inverse or not. This is sort of like the horizontal line test, but for linear transformations, right? It says your linear transformation can be one-to-one. The way you check it is to look at the kernel. All you need to do is answer, is the kernel 0 or not? And if it's 0, then you know that your transformation is one-to-one. Yeah.
What does it say there, since?
Since the kernel of t is
Okay.
0, sorry. Okay. So, okay. Another idea. I should have said earlier that another term for one-to-one is injective. Injective. So you may see this. You may see this term instead. Another related term. Another related idea is the notion of onto. So again, you have a linear transformation. You say t is onto or surjective if the image of t is all of w. Okay. If the image of t is w. Okay, so just to give some examples to illustrate what we mean by this, if I look at t sub pi over 4, the guy that's rotation by pi over 4, okay, or rotation by any angle, frankly. Then my set of outputs is the whole space, right? This is a map from V, from R2 to R2, from R2 to R2, and you see that my outputs cover the whole space, right? Any vector over here, I can get as an output, right? If I want, this vector, right? Well, I see that this guy over here, when I rotated pi over 4, gets mapped to it, right? Whatever vector I have over here, I can find some vector over here that gets mapped to it. Okay, so this is an onto map, right? This is onto. Okay, for a non-example, we use again the projection map. So t of xy equals x comma 0, right? So this thing, right, you see that its outputs all lie on the x-axis, right? And so this is not onto, right? This is not an onto map from R2 to R2. It's not onto. Right? Because I can't, if I want to get this vector, I can't get this vector as an output, right? So I don't get the entire vector space. Is that clear? Everybody getting that? Yes? Yes. Okay. Now I should say, watch this, everybody, please pay attention. So I should say that this example can be sort of fixed in some way. We can make it into an action. So if I let V be all of R2, and I let W be the x-axis, right? I let W be the subspace here, right? Then in that case, T, if I think of T as a map from V to W, it is onto, right? It's onto this subspace, right? If I think of T as a map from V to V, right, from R2 to R2, it's not onto, right? But if I think of V if I think of this as a map from V to W, it is onto. Okay, right? Because everything, right? Any vector in this subspace, well, I can get them, right? I can get it, right? So it actually depends on how you describe it. Okay, right? From here to here, this is not onto. From here to here, it is onto. Okay, is that all right? Clear? Okay. Okay. Oh yeah, maybe I should do another example. So from V a vector space, and V1 Vn basis, then the coordinate map from V to Rn, taking your vector to its coordinate vector, well, that is onto, right? That is onto, right? Because any set of coordinates here, I can get. Is that clear? Any set of coordinates in Rn, I just make their linear combination over here, and then that's the thing that has that coordinate vector, right? Right? So to get C1 to Cn, just let V be C1 V1 plus Cn Vn. Then the coordinate vector of that guy will be C1 through Cn, right? So if I want to get some vector, I can easily make up something that has that output. Okay. Okay. I'm going to have you try another exercise. So let A be a square matrix, and let T sub A be the map from Rn to Rn, the one that we defined last time, right? Left multiplication by A. So you have the square matrix, and you have left multiplication. You have the linear transformation. That's left multiplication. Then the claim is that TA is onto if and only if A is invertible. TA is onto if and only if A is invertible. Okay, and I'll give you a hint. Actually, you could do this in multiple ways, but I'll give, if you want, one hint could be use the rank theorem. Okay, actually, let me, since we're kind of running out of time, let me do this for you. Unless somebody knows it already. Does somebody have an idea? I was going to call on you, Yok. Yeah, Zia. Zia. Go ahead, Zia.
Since TA of B is an Rn, never mind.
Okay. So here's one way to prove it. You'd say, well, look, if TA is onto, that means that given any B in Rn, you can find X such that AX equals B. Right? We can find an X such that AX equals B. Right? Because we can find, such that TAX equals B. Right? In other words, that's saying that the dimension of the column space of A is n. Right? That we get all of Rn as the outputs. Right? That's the same thing as saying that the column space is all of Rn. Column space of A is all of Rn. But that means that the nullity is 0. Right? The nullity is 0 by the rank theorem. But that's the same thing as saying that A is invertible. And all these things are, Is that all right? Okay. Notice that being invertible is actually equivalent. Actually, we could. I don't know if it's completely obvious, but being invertible is equivalent to T of A being 1-to-1, right? So in this case, being onto and being 1-to-1 are the same thing, right? For a square matrix, being onto and being 1-to-1 are the same. Okay. Okay. Let me just introduce one last idea, and that is what happens when you put these two things together. So, if you have T, a linear transformation. If T is 1-to-1 and onto, if it's both 1-to-1 and onto, we say that T is an isomorphism. Isomorphism. Okay. Iso means same, morph means the form. Okay. So that what it's saying is that these two vector spaces are basically the same, right? And what you write is that V is isomorphic to W. V is isomorphic to W. So for example, again, the coordinate vector map, from V to Rn, taking a vector to the coordinate vector with respect to some basis, we saw that that was 1-to-1, and that's also that's 1-to-1, and that's also onto. So this map is actually an isomorphism. Right. The only thing that gets sent to the zero vector is the zero vector. Right. The only thing that gets sent to the zero vector is the zero vector, and it's also onto. So this is an isomorphism. Okay. In other words, what this is saying is that V must be isomorphic to N. So if V has basis So this is saying that any n-dimensional space, any n-dimensional vector space is isomorphic to Rn. I'm just going to close with one fact, so one theorem. If T is an isomorphism, so you have a linear transformation from V to W. If T is an isomorphism, right, in other words, 1-to-1 and onto, then there exists an inverse linear transformation, T inverse, going from W back to V. Okay. So there's a map that goes backwards, so that, in other words, T is a linear transformation, and T is linear. T inverse is linear. Sorry, and T inverse composed with T is the identity on V, and T composed with T inverse is the identity on W. Okay, we're actually going to use this fact, but I'm not going to prove it. So you could try it as an exercise. It's not too bad. But this is important. So if you have a map, if you have a linear transformation that's 1-to-1 and onto, it has an inverse map. Okay. But better than that, the inverse map, so it has an inverse map. That's not surprising, right? It's 1-to-1, it's 1-to-1 and onto. Right? It has an inverse map. That you could have guessed from pre-calculus. Okay. What's surprising is this part, that the inverse map turns out to be also a linear transformation itself. Okay. It's forced because the linearity of the forwards map forces the linearity of the reverse map. Okay. So, okay, that's it for today. Thanks for coming. Thanks for coming, everybody. Have a nice break.